Hi, here we are for Physics 1020 and 1090, the lecture for Wednesday, March 18th. We're still in Chapter 24 about wave optics. This is the fourth video of the Wednesday lecture and the last video for Wednesday. It's also the last video for Chapter 24. We're going to be talking about polarization by scattering and reflection. To begin, we have to go back and get an idea that we developed earlier in the semester about how oscillating or accelerating charges emit radiation. And suppose you have a charge, and that charge moves up and down like this. Well, that charge is accelerating, and an accelerating charge will give off radiation. And primarily that radiation will be given in the direction perpendicular to the motion of the charge. There will be some in a variety of directions, but right along the direction of the motion of the charge, there will be no radiation going up or down. It'll all be going out to the left and right. So that's the idea of a dipole radiation. Accelerating charge gives off radiation. We're going to use that idea to try to understand how you get polarization produced during reflection and during scattering. First, polarization by reflection. Okay, so you have electric field, electromagnetic radiation coming in and hitting this mirror. And it's polarized, plane polarized, so the electric field is going in and out of the paper. So drawn by these dots, circles with a dot in it, means electric field is in and out of the paper. As it comes down and it hits the mirror, so it hits a mirror down here, what happens? Why do you even get reflections off of a mirror? Well, the electric field in the electromagnetic wave oscillates all the charges in the mirror, and they're going back and forth like this. And those back and forth motion into and out of the paper are just right for releasing radiation perpendicular to their motion, which gives you this reflected ray coming out of the sheet. And that reflected ray also has the same electric field direction as the incoming ray. It's coming into and out of the paper. So polarization, polarized light, when the electric field's polarized into and out of the paper, gives you a reflected ray. No big surprise, we knew that light reflects off a mirror. Here's the surprise. You now have the other polarization state. Light's coming in, hitting the mirror, and its electric field is not into and out of the paper. It's perpendicular to the wave motion in the plane of the paper. So it's going like this. Okay, now, what would happen to cause a reflected ray? The light will come in, and it'll hit the mirror and cause the electric charges in the mirror to oscillate. And they'll be oscillating in the same direction as like this. Oscillations in this direction don't give off any radiation up in the same direction as they're oscillating. They give a radiation off perpendicular to the direction of oscillation. So what that means is you don't get a reflected ray. There's no reflection. So this polarization state gives you no reflected light. Now I should add that the fact that you get no reflection depends a little bit sensitively on the exact angle the light hits. So we're not going to worry about those details, but in general, the light comes in and this component, this polarization state, tends to have less reflection, or in some cases no reflection. So just to review that, if you had unpolarized light coming in, unpolarized light, it'd have both electric fields into and out of the paper, and also have electric fields in the plane of the paper perpendicular to the direction of propagation. It would come down and hit the mirror, and only those electric fields going into and out of the paper are going to produce a reflected ray. So the reflected ray is linearly polarized, even though the incoming light was unpolarized. So this is a way you can produce polarization by reflections. This is why we buy polarized sunglasses. A lot of times it's these reflections off of horizontal surfaces are a nuisance. If you're out on the water, this might be reflections from the surface of the water, or this might be reflections from a car driving by. There's a lot of horizontal surfaces that will give reflections, and for us they're a nuisance. They're just glare that we'd like to get rid of. If you buy sunglasses, you want to dim the light. What if you strategically dim the light by removing only one component, only one polarization state? You will dim the light in general, but for surfaces that are horizontal, you'll completely remove the light so that you can suppress horizontal reflections from horizontal surfaces. This is the whole idea of polarized sunglasses. You can also get polarization by light scattering. So we talked about light scattering before. Suppose you have the sun here and it's shining light into the earth, into the atmosphere. And here you are standing on the surface of the earth and you're not looking straight at the sun. You're looking up at the sky. Okay, now why do you have light scattering? Why can you see anything? Why don't you just see darkness if you're not looking at the sun? It's because the light that comes in is unpolarized. Some of the polarization state is electric fields going up, down, and some of the polarization state is electric fields going into and out of the paper. And it hits this air molecule. And as it hits the air molecule, it causes the air molecule to move. The electric fields accelerate the air molecule. The air molecule is going up and down, into and out of the paper. Well, the part that's going up and down is not in the direction that's going to cause electromagnetic waves to come and hit you. If you're going up and down, you don't emit radiation down along that direction. But the part that's going into and out in the page, you do emit waves coming down. So what you see is the light that's scattered by the air molecules comes down is linearly polarized. You see some polarization when you look up at the sky. Again, this process is not complete, but for the most part, you see light from the sky has polarization effects. And if you ever have any pieces of polarizer, you can look up at the blue sky, and you ought to be able to see as you rotate the polarizer around. The intensity changes because the sky is partially polarized. Let me talk about a couple other things before we finish this chapter. A couple other interesting features of polarization. Here you have linear polarization. Now, I want to look at this a slightly different way. Okay, first of all, light's coming straight at you, so it's propagating towards you, and we're looking at the electric field in a case of linear polarization. And instead of looking at different positions in space, I want to look at different instances in time at one position. So here we sit here, and the light's coming straight at you, and along one time, the electric field's going up. And then a little later, very short time later, like 1/4 of an oscillation later, the electric field goes down to 0. A little bit later, the electric field's going down. Electric field goes back to 0, and finally it's going up. So this is one period of the oscillation. So the electric field's going up and down, up and down, up and down in linear polarization. That's exactly what we saw before, just looked at in a slightly different way. You can also have the other polarization state. Here, the electric field is going right, left, right, left, right, left. And we look at what's happening in function in time. First, it's going right, then it goes to 0, then it goes left, then it goes to 0, then it goes back up to right. Now, you can combine those in kind of an interesting way. You can get what's called circular polarization. So initially, the electric field is going up, and then it rotates around and is going right, and continues to rotate, and a little while later it's going down, rotates more, a little while later it's going left, and then it finally gets back to where it started over here. This is called circular polarization. As the electric field comes at you, as the electromagnetic wave comes at you, the electric field is rotating around almost like a helix. Circular polarization. Now, if you think about this is really a combination of two linearly polarized waves. If you look at just the odd number of times, 1, 3, and 5, this is linearly polarized. You're going up, 0, down, 0, up. But if you look at the even numbered times, 2, 4, and then if you had 6 and past that, this is like linearly polarized horizontally, right, left, right. And you put these two together, and what the combination gives you circular polarization. You really have a combination of up and down polarization, right and left polarization, but this is crucial, they're phase shifted with respect to one another. So here's the peak where you get the maximum electric field up and down, and that's a different time than the maximum electric field going right and left. So two linearly polarized waves that are phase shifted relative to each other gives you this circular polarization. finally, I want to talk about some materials that have odd uh, uh, optical properties, and this is called birefringence. And an example of this is a crystal called calcite. Calcite is just calcium carbonate. It's a very common crystal. It's a transparent. If you just looked at a piece, you'd have a hard time telling the difference between calcite and just table salt. Now, if the electric field of an electromagnetic wave comes in from this side, and it's got unpolarized, so it's got electric fields going up and down, and it's got electric fields going in and out, and it hits the calcite, what's going to happen? Well, the electric fields that are going into and out of the paper pass straight through. Notice this hits it at a 90-degree angle, so that light is not expected to refract. It just passes straight through, comes out of the calcite, and it's polarized because the electric field is going into and out of the paper. That's called the ordinary ray because it behaves just ordinarily how you'd expect. The part that's linearly up and down, polarized up and down, hits this crystal, and it refracts. And it doesn't really refract as much as it just changes its direction because of the polarization. And then it comes out of the crystal and it's back to going straight across like before, but it's now polarized up and down, up and down. It's called the extraordinary ray because you wouldn't expect refraction at a 90-degree angle, but you get some kind of refraction anyway. So what happens is if you looked at something, some point here, a little point giving off light, you end up seeing 2 points come out of the calcite. You'd see a point that is an ordinary ray and a point that's an extraordinary ray. And if you use some polarization paper, you'd find that you could find one ray with one orientation of the paper and the other ray with the other orientation because these are different polarization states. So if you take a piece of calcite and you just set it on top of some text that you're reading and you look down, you actually see 2 copies of every letter. And if you use polarization sheets, you'll find that one copy has one polarization state, one copy has another. So this is a birefringence. So that concludes our discussion of polarization, and it concludes our discussion of wave optics. So in the next chapter, we're going to move on and talk about some optical instruments. In particular, we're going to talk about telescopes and microscopes, and we're also going to talk about our eyes.